This problem asks to describe the preparation of 40 liters of 0.02 phosphate buffer pH 6.9. Very practical problem in the lab. We always need a phosphate buffer. And this part A asks to start from 2 molar phosphoric acid and 1 molar KOH. Let's write down the details, okay? So again, this is problem 38 in Siegel, number 38, and this we can find it in page 92. Ask us to prepare 40 liters, a little bit high volume, but very practical otherwise. 0.02 phosphate buffer, and the pH for this phosphate buffer they want is 6.9. And they started with 2 molar solution of H3PO4 and 1 molar of KOH. Obviously, you are going to make a phosphate buffer. If you put phosphate in water, it's going to be a lower pH because it's an acid, right? So that we want to increase the pH by KOH. But how much KOH do we need? That's the most important part of this problem. First of all, for phosphoric acid, this is a phosphate buffer. All source of phosphoric acid comes from this H3PO4 here. I don't care what's the species that is going to be prevailed there, what's the equilibrium there, but all the species coming from H3PO4. So first of all, for H3PO4 is a very simple calculation. It's a dilution. So it's based on this formula, M1V1 equals M2V2, right? So we are going to start with 40 liters. We're going to finish with 40 liters of 0.02 molar. So let's start in here. So my final that I want is 0.02 molar, and I want 40 liters of this buffer. And I'm going to start with 2 molar of this H3PO4, and I want to know which volume I'm going to need for that. So therefore, we have here, the volume is going to be 40 times 0.02 divided by 2, which gives us 0.4 liters or 400 milliliters. Okay, so that will be what you need. However, if you take 400 milliliters of phosphoric acid and you put in water and you dilute it to 40 liters, the pH is not going to be any closer to 6.9. Now we need to know what to do in order to have that pH adjust to 6.9. So let's write down the equations of the equilibrium for phosphoric acid. We start with H3PO4, which gets in equilibrium with H2PO4 minus plus H plus, right? And there is a Ka1 in here, or pKa1, which I already have that value. I can get directly from the book here, 2.12 from the Siegel, or it can be given in a test. And the second equilibrium would be H2PO4 in equilibrium with HP2O4 minus with HPO4 2 minus plus H plus. This would be the pKa2, which would be 7.21. And finally, the last part of the equilibrium, that's HPO4 2 minus, is going to be in equilibrium for PO4 3 minus plus H plus, and the pKa3, which is 12.32. 12.32. All right. So now, if you want your pH, to be 6.9 as required by the problem, so the closest equilibrium that we have here is this one. So therefore, your whole story here is going to be based on the equilibrium of this stage in here. So the second stage is the most important one, right? So what you want to do to make a solution of pH 6.9 is to have the right concentration of H2PO4 minus and HPO4 2 minus. These two species in here, you want to adjust the concentration for what you want so that pH becomes 6.9. How do you go about to find what the concentration of these species are? We have an equilibrium here. We know the pH, we know the pK for this equilibrium. This is a very simple application of the Henderson-Hausberg equation, which in this particular case in here would be pH equals pKa2, right? Because it's the second step of the equilibrium that we're talking about, plus log of the concentration. In this case in here is going to be HPO4 2 minus divided by the concentration of H2PO4 minus, correct? Okay, so we just plug in the numbers and calculate that. So let's do that. Let's plug in the numbers and calculate this. So pH is 6.9, pKa is 7.21. So now we can calculate the log of the concentration of HPO4 2 minus over the concentration of H2PO4 minus. Okay, so a little bit, let me move this thing a little bit up so that we can have more space to continue work on this one. So this is going to be 6.9 minus 7.21 equals log of that number there of the HPO4 minus divided by the concentration of H2PO4 minus. So from here you can say that the concentration of HPO4 minus divided by the concentration of H2PO4 minus is going to be 10 to the power of this number here. This would give a negative number, 0.31. So we're going to put here 0.31. Okay, so then we can calculate the ratio between these two, and 0.10 to the power of negative 31, change sign, the power, it's giving 0.489, 0.49. Okay, so that's the relationship between these two concentration when the pH is exactly 6.9. Let's move up a little bit more to get more space. And now we have the ratio here of the two species. We now know that HPO4 2 minus equals 0.49 concentration of H2PO4 minus. Correct? Just doing some algebra here. What other equation that we have? We have two unknowns here, and we have only one equation. We need a second one. The second equation that we have is that we know that the concentration of the buffer is 20 millimolar, 0.02 molar, right? So we can say that the concentration of HPO4 2 minus plus the concentration of H2PO4 minus equals 20 millimolar. Remember that was 0.02 molar. It's the same thing as 20 millimolar, right? Correct? Okay, so now let's plug in these numbers here because we have HPO4. We know that this one here is the same, and we can replace with that one. So you can say 0.49 H2PO4 minus plus H2PO4 minus is going to give it equals 20 millimolar, right? So from here, we can calculate the concentration of H2PO4 minus. It's going to be equal to 20 millimolar divided by 1.49. 20 millimolar divided by 1.49. Very simple algebra here. 20 millimolar, 20 divided by 1.49. It's going to give us 13.4 millimolar. 13.4 millimolar. 13.4 millimolar. So the concentration of the other species is going to be the difference for 20, right? So the other species, which is HPO4 2 minus, HPO4 2 minus, the concentration is going to be 20 minus 13.4. 20 minus 13.4, which give us 6.6 millimolar. 6.6 millimolar. Okay? Now, how much KOH I'm going to need in here? So I know exactly what I have. So the first thing I have to do is to add the KOH enough to bring this first reaction. Let me highlight it here. First thing I have to do is that to pick up my H3PO4 and make it H2PO4. For that, I need 1 mole equivalent. So I have to calculate how many moles of H2PO4 I have to calculate this number of moles of KOH that I need. Okay. Once I have H2PO4, then I need to add more potassium hydroxide to make some of the H2PO4 becomes HPO4 minus, because I want some of this to be 6.3 here. There is another way of doing this thing too. There's not a single way for doing any problem, right? There's multiple ways. Another way, instead of that, we could calculate directly here by the number of moles that we have for H2PO4 minus that one based on this concentration of 13.4 millimolar. But let's do one of the two ways, and let's find the solution here. So let me scroll up a little bit more so that we have more space for doing that, and let's do it now. So the number of moles of KOH that I need to get the H3PO4 to H2PO4, to write this thing down to make it very clear. What I'm calculating here is that the number of moles that I need to pick up H3PO4 to make it H2PO4 minus. I'm not care about the balancing between the two species yet, okay? Just I'm going to add phosphoric acid, and I want to add potassium hydroxide to remove 1 proton. So the numbers mole is the same based on the number of phosphoric acid. So how much phosphoric acid did I add in here? The number of moles of phosphoric acid that I add is going to be the molarity times the volume in liters. So the molarity is 0.02, and the volume of the solution is 40. So we have 0.8 moles of H3PO4 were added to this buffer, right? From the beginning. Now, if I wanted to remove and it becomes H2PO4, I need the same equivalent number of moles of KOH. So the number of moles of KOH that I need just for this step again is equal 0.8 mole. And how do I get 0.8 mole of KOH? KOH comes in the form of a solution, right? 1 molar solution. So let's keep the number of moles for the time being. And let's calculate the number of moles that we need now to pull KOH from the H2PO4, the number of moles that we need of KOH to pick up H2PO4 minus that we already have above, and pull it to becomes HPO4 2 minus, right? So what's the number of moles that I need in here? Here, what is important for this calculation is the concentration of this species in here, right? HPO4, right? For each mole of HPO4 2 minus, I need 1 mole of KOH. So let's calculate the number of moles in here. The number of moles in here is going to be the same thing. The molarity, which is 6.6, but in millimolar, so I'm going to put 10 to minus 3, times the volume, and the volume is the same. The volume is 40 liters, okay? So this is going to give us 6.6 exponential 3, change sign, times 40. There's going to be 0.264. 0.264 mole. Okay, so the total number of moles of KOH that I need is going to be 0.264 plus 0.8, which is total, okay, is going to be 1.064 moles of KOH. How I get 1.064 moles of KOH? I have a solution that's 1 molar. That was given in the beginning of the problem. So if I have a solution, I can calculate the the volume of that solution. I'm going to break this thing down here so that we remember that very nicely. Molarity divided as number of mole divided by the volume in liters, right? So therefore, the volume in liter is going to be the number of moles divided by the molarity. In this case here, there's no way that you can make a mistake because the molarity is 1, but in other cases we may get in trouble, okay? So 1.06 divided by 1 gives us 1.064 liters, or equal 1,064 milliliters of this solution. Okay, so how do you prepare this bath again? How much volume we need of phosphoric acid? Was 400 milliliters of phosphoric acid we calculated in the beginning. Now we add 1,064 milliliters of KOH. How do you prepare it in practical terms? This is the solution for the problem. But in practical terms, we will put a huge volume of water because this is 40 liters, right? We will put a very large volume of water. Then we put 400 milliliters of phosphoric acid. That's what we need for that. Then we start adding little by little potassium hydroxide up to 1,064. And finally, we adjust the volume for 40 liters. But in terms of the numbers that we have to calculate for a solution in a class or in an exam, the number of moles, the volume would be 400 milliliters of phosphoric acid, 2 molar, and 1,064 milliliters of KH, 1 molar, and the final volume is 40 liters. It's very simple. A little bit of calculation, but very simple and a very practical problem for the lab. Thank you for watching.